This pendulum motion is called a mathematical pendulum. In previous physics, this movement is only approximately described for small deflection angles. And this method no longer applies to larger deflection angles. And how this movement took place physically has never been explored. The question is why the pendulum can move back and forth against gravity through the lowest point and upwards. You could say because the pendulum has the kinetic energy. That is not entirely true, because energy alone cannot work against force, at least not directly. The correct answer is inertia, which is understandable. But how the inertia works in detail, nobody knows yet. Now we would like to explain it through this movement. If you let go of the pendulum at point A, Earth gravity accelerates it downwards in a tangential direction. Against this, the body uses inertia to insist on its state. With increasing speed, the inertia increases, while the driving force F decreases. At each point B, for example, the inertia is balanced with the driving force F. Below point B, the driving force F is smaller than the inertial force. Because in order to accelerate the body further, it needs a driving force that must be greater than the inertia of the body. Therefore the pendulum cannot be accelerated any further and the speed remains unchanged up to point C. So the pendulum reaches its maximum speed at point B. This movement from two opposing forces can be described with this equation. After reshaping the following results. So this equation can be solved for V. From this we get the speed of the pendulum at the point with the angle theta. Assume that the angle at point B between the rope and the vertical is theta, at which the inertial resistance is exactly as great as the driving force F. Then the following equation results. Assuming the radius r is 1 meter, this equation gives the result. So at point B with the angle of 43.1 degrees the speed of the pendulum reaches its maximum. Below this point, the driving force is less than the inertial resistance. As I said, in order to be able to accelerate a body, it needs a driving force that must be greater than the inertial resistance of the driven body. Therefore, the speed cannot increase any further. Then this maximum speed remains unchanged up to point C. At point C the driving force F is 0. The pendulum runs smoothly through point C at its steady speed. After point C, the force F works against this movement. As I said, also to slow down a body, it needs a braking force that must be greater than the inertial force of the moving body. Because at the beginning the F is smaller than the inertia, the speed cannot be reduced after point C. Only at point B*, the symmetrical point of point B, at which the F compensates for the inertia again, the inertia is exhausted. But exhaustion does not mean that the inertial force disappears, it continues to oppose the driving force as long as the body continues to move. From B** upwards, the driving F is greater than the inertia. Because part of the driving force is further balanced by inertia, only the remaining part remains, with which the speed of the pendulum is reduced. Then the inertial force decreases permanently with the ever-decreasing speed. Nevertheless, it always compensates for part of the driving force until the speed is reduced to zero. That is the physical process of that movement. The role of inertia in this process is that the mass body can move as freely as possible. With inertia, the body remains at its speed. We see that the speed of the pendulum from B to B** is practically constant. To determine this speed, we insert the appropriate values in equation, asterisk, and solve them, we get the speed at point B. Of course, air resistance is not taken into account here. But now we have a problem, because according to the law of conservation of energy, the potential energy at point A should be equal to the kinetic energy at point C. From this, however, the speed at point C results as follows. There is a big difference between these two results. So if our calculation is correct, it somehow calls into question the law of conservation of energy. About this one could say very loudly, any interpretation or theory that does not fulfill the law of conservation of energy is simply wrong. Any attempt to refute this iron proposition, the law of conservation of energy, is apparently pointless, at least at the present time. Then we have to put this topic aside for now. Thank you very much for your attention. See you next time.